Hello everyone, welcome to Chapter 3, Derivatives, and the focus of today's section will be derivative as a rate of change. We have seen derivatives in different forms, and we were introduced that derivatives can be interpreted in 4 ways. And the first one was that it could be a slope of a curve at a point, or slope of a tangent line at that point, or slope of or the rate of change. And so we are looking at the derivative as a rate of change. Okay? And what that means is that the slope that we've seen before, slope of a curve, which is the slope of the tangent line, the other name for it was derivative. That's the 4th version. Right? And we saw that the derivative was nothing but limit of the dq, so limit of the slope. And here we're talking about rate of change. We've seen rate of change. Rate of change is y2 minus y1 over x2 minus x1. How fast does y change with respect to x? But when we talk about derivative as a rate of change, then we actually mean the instantaneous rate of change. What does that mean? How quickly does y change with respect to x at every instant? So then this instantaneous rate of change will measure the rate of change at an instant. And in math, when I say at an instant, then I'm giving a specific x value where x is specifically x naught. And this is what we saw previously. We said, well, derivative at a point would be f prime of x naught, which is the limit as h approaches 0, f of x naught plus h minus f of x naught all over h. Right? And from here we actually, in another section, we saw how we could find this not just for a point, but for the entire function if we can find the derivative at every point of that interior, of that function between a and b. The interior point between a and b, where you can find, we use the idea of continuity and all that to establish it. Now we want to come back to finding the rate of change at a point, because that here would translate as instantaneous rate of change. Therefore, the whole approach to derivatives would move away from pure math perspective into application perspective. So you'll see a lot of problems related to physics. And we always see a rate of change of y with respect to x. But here we will be starting to look at the change in y with respect to time t. Because when we say at every instant, we're talking about the time. And therefore it becomes practical in physics particularly, where we always try to see the change with respect to time. We could have it with respect to anything. Right? We could have change of area with respect to diameter if it is a circular spread. If you are, say, blowing a circular balloon for some reason, you could then relate the area, because as the circle of that balloon increases, the area increases, right? So what is the speed in which the area of the balloon increases as the diameter increases? So you can go on into any aspect or any application of this problem using the idea of instantaneous rate of change. So let me put up the first question. the area A of a circle is related to its diameter by the equation A equals pi over 4 d squared. So the area and the diameter are related. This is not new because we know that the area and the radius are usually related. That's the usual form we see. But we know that the diameter is again related to the radius because diameter is twice the radius. And if you want to recall what that is, you know that the center of a circle and the radius are usually important factors for us to even describe a circle. Now, if you went from end to end through the center, then you have the radius here and the radius here, right? This is the radius and this is the other radius. So 2r, okay, is your diameter. So if you go from end to end, this whole thing is your d. 2r is your diameter. Okay. So we know that the area of a circle is pi r squared. We've seen this. But you remember that r is, if you want to rewrite this in terms of d, we know that r is d over 2, diameter. Half of the diameter is your radius. So pi times diameter over 2 squared. I'm replacing the r with d over 2. So that is pi d squared over 4, which is the same as pi over 4 d squared. So if you look at this expression here in the problem, it's not something new. It's just derived by replacing the r in your area formula by d over 2. Okay. So that's a quick side story. Now let's come back to the question. How fast does the area change with respect to the diameter when the diameter is 10 meters? So we want to first analyze the question. How fast is an indication of the rate of change, right? Rate is the speed, so something's moving fast. So how fast does the area change with respect to the diameter? So a quick connection to you is that if I wrote dy over dx, it implies that y changes with respect to x, right? That's the understanding. That's how you would interpret it. Here it says, how fast does the area change with respect to the diameter? So area with respect to diameter, and please watch out for the case sensitivity here. Area is always capital A and diameter here is capital D. This implies area changes with respect to the diameter D. And so I just interpret what I have here in the problem with respect to the derivative format. Okay. So all we are asked to do is find the derivative of A with respect to D. So we already have A to be pi over 4D squared. Let me separate the space here so we don't spill into it. And so now if I have to do, if I have to do dA over dD, D is the variable here. So previously we would have had x, but here it's D. So if you want to make sure that you take the derivative of this pi over 4D squared, that's how we did, right? We replaced the function A with the expression associated with it. Pi over 4 very clearly is a constant. So pi over 4 needs to be pulled out and you take the derivative of just the d squared. So now we can use the power rule and say, okay, pi over 4 is pulled out times d squared will be 2 times d power 2 minus 1. You'll have to adjust your mindset here to reflect the different variable we have. So don't get too fixated on the x variable. So this is the same as x power n. So it's n, derivative of that will be n times x power n minus 1. Instead of x, we have d. All right, so that's pi over 4 times 2d, and then simplify this. I'm again going slowly just because I want you to get used to the new variable we're using here. And that will be pi d over 2. This is your derivative of a with respect to d. All right, we found that portion of it. But it says, how fast does the area change with respect to the diameter when the diameter is 10 meters? So here we found the derivative of the function, but we need to find the instantaneous rate of change. Instantaneous rate of change obviously has to be for a specific instant. And that specific instant is when the diameter is 10 meters. Now diameter keeps increasing. At one particular point, at one particular instant, it is 10 meters. So we are looking at it for a specific instant. The way we express that is we put this vertical bar and say when d equals 10. This is kind of a shortcut for us to say we are finding the derivative, or we are finding the rate of change of area with respect to diameter when diameter is 10 meters. So then I go into the formula, and in the place of d I now have a specific instant which is 10, and then I substitute that for d. So the answer comes out as 5 pi, and because it's a word problem we have to be very particular about the notation we use. Okay, so it is area with respect to the diameter. The area is meter squared per meter. Okay. Or if they wanted it in decimal values, 15.71 meters squared per meter. I hope that clarifies the application side of it. Now when we talk about the physical application, we always are interested in seeing how a body moves, an object moves, and how to track its position. Because in physics, we'd like to track, say, a celestial object in the sky. How does it position? So that's how we read the stars, the constellation, all that, right? So we are tracking the position of the movement of the Earth and other celestial bodies. So there must be some kind of a reference to do that, right? So if we want to track an object, okay, and we can use the XY grid, okay, because then it makes it easy to make the location clear, because obviously an XY grid offers unique location, right? Two different points will have to point to two different locations. They can't be pointing to the same location. And so we can see that the uniqueness of a point really helps us on an XY grid. So let's say an object moves along a horizontal line, okay, and we can say that the object moves from S1 to another point S2. Okay, it's moving along a horizontal line, so you can see that this is the object was first at S1 and then it moved to S2. So it moved this distance between S1 and S2. So again, in physics, we like to use this triangle symbol, delta S. Triangle symbol actually is a Greek letter, okay, and it's pronounced delta. To write the D properly. So delta S means change in S, change in the position. Okay, so here this means change in the position of the object with respect to time, of course, right? But right now we're only talking about the change in the position. It changed from the position at S1 to the position at S2. And so this change is what we are really interested in physics. And S is the traditional letter that is given to the position of an object. Okay? And so if you can consider this distance between S1 and S2 as delta S will be S2 minus S1, right? So this delta S, let me write that out here, which is S2 minus S1, is the difference in the positions of the object. And there's a name for this delta S. It's known as the displacement. Delta S is called the displacement. Now remember, this is physics, right? So this can be applied in different medium, and therefore we use the language displacement to say that something got displaced or moved from one place to another. Typically, we are interested in knowing how it changed with respect to time. Therefore, the position of an object is usually written as a function of time. So S is usually a function of time, f of t. Okay? So then let me write that out here, that position of an object is a function of time. This is typically the way we write the function. So if you took the first derivative, s prime, which is the same as f prime of t, you know that that is the first derivative if you use the interpretation of the symbol, right? But we also know that the first derivative here would just mean the rate of change of the position with respect to time. So rate of change of s with respect to time t, because we now know that s stands for the position of the object, so position with respect to time. Rate of change of s. In other words, how fast is the position moving? I'm sorry, how fast is the object moving? How fast is the position changing? That's what I meant to say. How fast is the object moving with respect to time? It sounds really lofty, but if you think about it, it's actually asking us, what is the speed or the velocity of this object, right? How fast is it moving? So I'll just write that in plain English. How fast is the object moving with respect to time? And you clearly see that if you were to interpret this, you're just basically looking for the velocity, right? So if you took the derivative of the position of an object, you actually get the velocity. You can see how we can derive different meanings, layers of meaning to this. And that is where we really, really love the idea of rate of change that we learned in algebra, because we can relate it to so many real life circumstances. Here it is about velocity. And therefore, it takes a special notation, v of t. So position was s as a function of time, and v of t is now giving us the velocity. And one more notation is that v of t is nothing but ds over dt, right? If you use the d over dt notation, it's the derivative of s with respect to t. That's the rate of change. So you can make a number of relations from here. All right, how does it behave if I went for the second derivative? S double prime, which will be f double prime of t. That will be the second derivative. And we know that we are taking the derivative of velocity, because the first derivative was velocity, its derivative. So derivative of velocity. So now our question, if you were to write it in regular English, we say, how fast is the velocity changing with respect to time? Right? That's what this means. So how fast is the speed changing? Not how fast is the object changing. How fast is the speed changing? And if you change speed, what's the word for it in English? We accelerate, right? So acceleration is what you get if you took the derivative of velocity. And acceleration is written as a of t because it's with respect to time. And a of t is nothing but d squared s over dt squared, because that's the second derivative. Okay. You can also write it as a of t is nothing but dv over dt. It is the derivative of velocity, or you could see it as the second derivative of the position of the object. Right? All right. And what happens if you took the third derivative? Third derivative of t. So I'll just say third derivative And the question now will be, how fast is the acceleration changing with respect to time? Each time it's always with respect to time, because that's the one constant thing that over which we're seeing all these changes. So how fast? So how fast is the acceleration changing? So you are kind of picking up that speed or lowering that speed, and if you make changes to that, the word for that is actually jerk. I know it has a different connotation in the Western world, but here it's a nice word, jerk. Is that, in English, that's the word, jerk. You come to the sudden halt. So there was a jerk, and then you move on. So, that jerking motion, that is when you have changes in the acceleration. And so that's called j of t. And j of t can be written in so many ways. You can think of j of t as d cubed s over dt cubed, because it's the third derivative of, if you want a quick connection, acceleration is the second derivative, therefore jerk is the third derivative of the position. Or you could see it as the second derivative of the velocity. So it's d squared v over dt squared. Or it could be the first derivative of the acceleration, dA over dt. And I use small a because it refers to the acceleration, which is lowercase a. Capital A, we used it for area, so please be careful about the notation here. And so you can see how we can come up with all these interpretations, particularly in higher orders of the derivatives. Okay. Now, because we're talking about how fast, if you have a positive value, right, it's increasing. If it's a negative value, it's decreasing. That's what we saw in math. Therefore, when we particularly talk about velocity can be positive or negative. It can take a positive value or a negative value. But when we use the word speed, we tend to think of them as the same, velocity and speed. Remember, in application, particularly in physics, speed is absolute value of velocity. Meaning when I say speed, it can only be positive. And so you can think of it in real life too, right? The speed limit, it never says negative 45 miles per hour. Okay, even if you're going in the opposite direction, it always says in whichever direction you're moving, it always gives the measurement in the positive value. Because only that makes sense, just like distance, right? Distance can only be measured positive. Likewise, speed can only be measured positive. But when we use the word velocity, then we are allowed to go positive or negative to indicate opposite direction, movement in the opposite direction. Okay, so speed is absolute value of velocity. Now let's consider this graph. When we learn to read graphs and understand information from graphs, obviously the most important information is to see what your x-axis relates to and what your y-axis relates to. Here this relates to, the x-axis relates to time measured in seconds, and here it is v, the y-axis, so that's your velocity. And velocity is not the same as the position of an object, right? Velocity itself is how fast an object moves with respect to time. So velocity here is about the speed in our regular terms, but we know now that speed actually means positive values only, and the velocity is something that can go positive or negative, right? So we also have that information here. It says velocity is the first derivative with respect to time, first derivative of the function, first derivative of the position of the object. So keeping that in mind, when we say at time 0, v is 0, what does that mean? At time 0, there is no speed, right? And we can see that from 0 to 1, right, 0 to 1, the line is increasing, meaning the velocity corresponding to the y-axis, the velocity is increasing. So you can say that from 0 to 1, we sped up, right? And then if you look at the space between 1 and 2, from 1 to 2, you can see that the corresponding y value or the corresponding v value is the same. So v is constant, which means there is no increase or decrease in the speed or in the velocity of the object, which means it is moving steadily. And from 2 to 3, you see that the curve kind of drops, right? It's decreasing. So you know that the velocity correspondingly on the y-axis has reduced as well. So it slows down. But you know that this blue portion is where it moves forward because the velocity is positive. Okay. Now, once the graph goes below the x-axis, you know that all those values will correspond to the negative velocity, negative v. Therefore, we see that once you move, the portion that happens below the x-axis is where the object moves backward, okay? Or in this case could be the opposite direction. So it moves backward to indicate that it has changed direction. And so we now see that in this direction, right, the velocity picks up, so we speed up, and then the velocity slows down in the second half from 4 to 5. Now, from 5 to 6, you see that the curve actually coincides with the x-axis, like in this case, the t-axis. So, from times 5 to 6 seconds, from the 5th second to the 6th second, the velocity is 0, which means there was no speed, nothing moved. So, the object is still. Okay. So, you can think of this as if it was a car that was moving, right? So, if you think of that, the car sped up, then it was maintaining a constant speed, then it slowed down. Then it turned direction, it made a U-turn, let's say, and it went in the opposite direction. It sped up and then it slowed down. And then you can think of this 5 to 6 as if it was, waiting at a signal. And so it's waiting for the lights to change, and that is the reason could be that the velocity is 0. There was no movement because the car didn't move. And then you can see from 6 to 7, the car sped up again. At this time, it changed direction and it came back to that same route. And now it's going forward again. Yeah. So the whole idea of this is that we're able to interpret this by understanding that the direction can change when we talk about velocity, and the graph here captures the speed, not the position of the object. Okay. So it really makes a lot of sense. Now, if we say rewrite this whole thing, this velocity, instead as a speed, that means this blue portion that is happening below, I should say this pale orange shaded region, right? That has to be flipped to the space above on the x-axis. It should go above the x-axis if we want to talk about the speed, because speed can only be positive. But when they say greatest speed, we're talking about the absolute value. The absolute value of v would give us the speed, right? So if you want to see the greatest speed, you want to see the peak that it reaches, and the peak can be up or down, because when you take the absolute value of the velocity, you get the speed. So the greatest speed in this case would be the speed that happens here, because that will correspond to a negative v value, but with the absolute value, that negative is returned as a positive value. So your speed is measured. All right, now let's go into a problem where we kind of try and understand how to calculate velocity and things like that. A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160t minus 16t squared feet after t seconds. We have A, B, C, and D. We'll get to that. So we have this rock that's blasted, and so it blows this rock straight up. So you can see the picture here. The rock goes straight up, and it goes up, and then it reaches a certain height, and then it falls back, right? That whatever goes up comes down. So we have that information here just as a drawing to capture the information. Now, what we're told is that it launches with this initial velocity of 160 feet. But we have that information actually given to us in the equation. It says s equals 160t minus 16t squared. Okay. S is the height, because it says the height of s. Okay. So let's quickly make a note of that. S is the height measured in feet, and t is the time, of course, but it's measured in seconds. You can see that after t seconds. Okay, so we have these, we need these to interpret our answer in the end. So S here is the position of the object. In this particular case, it's the height. The position of the object corresponds to the height. Okay. So when S is 0, that's when the rock is on the ground, and so it just launches, and then it reaches some maximum height. So we have S max. It reaches some maximum height, where it goes to that height, and then it pauses because it has no more steam to go further up. So it has to now start falling down. And so when it momentarily changes direction, right, it has to have a velocity of 0, and that is what is captured here. And then it falls back down to the ground. Okay. Now let's go here. It says, A, how high does the rock go? So there are two ways to look at this. So this is how you draw the graph. But if you look at the equation given to us for the height in feet, it's a quadratic equation. And from what we know, if you were to rearrange this, I'll use the other color, yeah, you have negative 16t squared plus 160t, right? I'm just rearranging the terms so that I have the highest degree occurring first. So you know this information right here tells you it's a parabola that opens downwards, right? That's because of the negative leading coefficient. So it opens down, which means if you were to graph this, it is it's as if your graph went, your rock went from 0, right? This is let me mark this as T, and this is my S. So T0, S0, that makes sense. Then it goes up, it reaches a maximum height, and it should come down. Can't go below that, sorry about that. Can't go below the ground, right? Just to reach the ground. So this is my S equals 160, or I'll just write 16, negative 16 t squared plus 160 t. Because it opens downwards, we do know that the vertex, the highest point of the graph, would be that. And that point corresponds to S max, right? Because the vertex is going to be t comma S max. For some time t, it's going to hit a maximum height. So that is what we need to figure out when it says how high does the rock go. We know that our focus is on finding that S max. Okay. So let's talk about A then. Part A is, we just reasoned out that S max is how high the rock can go. So then this implies that at S max, if you look at this diagram here, at S max the velocity was 0 because that's the maximum height after which it falls, and so it has to pause to turn directions, right? So this implies S max is when velocity is 0. And we know velocity, which is v of t, velocity is a function of time, is nothing but the first derivative of s. So the first derivative of s must be 0. That's what we're saying. S max happens at that when the velocity is 0. So then you go ahead and find v of t, which is the first derivative. So come back here and then take the derivative. Okay, you can take it in any way. We'll just go by how it is presented in the problem. So I'm going to look at it as 160t minus 16t squared. So derivative of this would be 160 minus 16 times 2t. So let me write that here. And that is set to 0. Okay. So then this means it's 160 minus 32t, that's equal to 0. Solve for t. That means t is 5, but we know t is measured in seconds, so let's say 5 seconds. So now you have to come back and interpret this. So this implies 5 seconds after the blast, the rock will reach the maximum height, right? the rock reaches the maximum height. Notice how you understand the circumstances and kind of reason out as to what would happen when it reaches a maximum height, and the biggest clue we used was that the velocity will be 0. From there we were able to pick up the idea of finding S max when the velocity is 0. Even now we haven't really found S max, we only found the time when it reaches that maximum height. So this implies that I have to find the height when t is 5. So in my given equation, wherever t occurs, I have to plug in for 5. And so compute that. That gives you 800 minus 400, which is 400 feet. So we actually found S max is equal to 400 feet when the time is 5 seconds. So the actual answer was 400 feet. So don't just stop with t equals 5, because that only is needed to help us to get to the S max. What about the second part of the question? Part B says, what are the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? So then we are looking at this information. You know that the maximum height, we just found this to be 400. So you will cross 256 feet on the way up to 400. So the rock crosses 256 feet on the way up and on the way down. So they're asking us to find the velocity and the speed of the rock when it is at that particular height. So let's come down here and say they're trying to respond to B. So we need to find the velocity. We must find the time it takes. Because once we find the time, we can plug that in the velocity function and find the velocity. So we need to first find the time it takes to reach that 256 feet up and down, up and down. All right, so let's say that the height is now fixed to be 256. T equals what? So for that I have to call upon the S function. S is 160t minus 16t squared. This is given to us. And we're fixing this S to be 256. So you're setting this equation to 256. Therefore, it now becomes a quadratic equation. Let me just write this out one more time. 160t minus 16t squared, and I subtract 256 on both sides, and that gives me that. Right? Now rearrange the terms because it's quadratic. I want to factor out a negative 16, and I want to keep the t squared term first. So it's t squared minus 10t plus 16. Your GCF, greatest common factor, is 16, but I want to pull out the negative because then it's easy for me to factorize it. Remember, we always factorize quadratic equations, so for that matter polynomials. So in particular, for this being a quadratic equation, this means that it's t squared minus 10. Negative 16 cannot be 0 because negative 16 is negative 16. Can't be anything else. So that means this other factor is the only one that can be 0. Now factorize this using the x method, or the we call it the BC method, or you know, if at all they fail, you can use the quadratic formula. But this one here is pretty straightforward. So you get the two factors to be 2 and 8. So t minus 2, t minus 8, which is equal to 0. And then set each factor to 0. So t minus 2 is equal to 0, or t minus 8 is equal to 0. From zero factor property, that means t equals 0 or t equals 8. We'll choose one or the other, but here in this case, both these answers work because it crosses that 256 feet on the way up when it's 2 seconds and on the way down after 8 seconds. Okay. So we'll find the velocity when it's 2 seconds up. That will be 160. So remember velocity. So let me just put v of t first. Velocity. We found this in part A, right, where we took the derivative of the s function and we got 160 minus 2t. So this is where I'm going to plug in for different t. So when t is 2, that was 32t. I just put the 2, or only the 2 appeared. So let me fix that there. All right. That's 160 minus 32 times 2. Okay. 160 minus 64, which is 96 feet per second. Remember, it's velocity, so it's the how fast the position changed, the height changed with respect to time. So it is feet per second, and this was for way up. And then when it's returning after 8 seconds, plug that in as well. 160 minus 256, negative 96 feet per second. This is on the way down. So those are the velocities. So clearly we know that they can take different signs. And it makes perfect sense because the positive velocity is the way up, and when it changes direction, the negative velocity indicates the way down. Okay. And we are asked to find the speed. Speed will be absolute value of v of t. So absolute value of v of 2 gave us 96 feet per second, as well as absolute value of v of 8 would also come back or return a positive value of 96 feet per second. Okay. So we got these two. Then we go to part C. What is the acceleration of the rock at any time t during its flight after the blast? What is the acceleration? Recall that acceleration is the derivative of the velocity. How fast is the velocity changing? That's what it means to say, what is the acceleration? So, using our derivative idea, we can always calculate that and say acceleration a of t is v prime of t. So, we just use the v of t here, right? V of t. So you're taking the derivative of this v of t. So derivative of 160 is 0, because derivative of a constant is always 0, minus 32. So velocity v prime of t is a negative 32. So it's basically negative 32 feet per second squared. Right? And there is no t involved in this. It's a value. It's a negative value. It's acceleration due to gravity here. And so we see that the acceleration is constant. That's very interesting because we didn't have any external factors affecting it. And let's go for the last one, D. When does the rock hit the ground again? It started from the ground, right? So it went up and it comes back and falls back to the ground. So when does it hit the ground again? So think about this. When does it hit the ground? S indicates the height from the ground, right? When it hits the ground again, quite obviously the height will be 0. So when the rock hits the ground again, S will be 0. So let's write that information out here. So we'll say the rock hits the ground at a time, when S is 0. That makes perfect sense. So this implies your S, which is 160t minus 16t squared, is set to 0. Now if we can find the t, that will help us to locate the time when it is when the height is 0. So once again, factor out negative 16t. You get t minus 10. I put the order around, okay? So I put the t squared first and then the 160t, so we got that. This implies negative 16t is equal to 0, or t minus 10 is equal to 0 by zero factor property, and that implies t equals 0 or t equals 10. T equals 0 makes sense because this is when the blast occurs 0 seconds, and this information is when the time taken for the rock to fall back to the ground. So then, although I have two t answers, I will choose the one that makes sense in for this section, part D, which says the rock returns to the ground ten seconds after the blast. So we saw the application in physics, right? A real-life application. Can we find or can we use the rate of change in some other field? Of course, we can use it in biology, physics, chemistry, geology, anywhere. And so the most famous other place where we use it is in economics. And here the derivative, what we call as derivative in math, and what we like to refer as the rate of change in physics, is actually called the marginal cost of production. When it comes to the cost of producing units, okay. So then if C is considered the cost function, and let's say X refers to the number of units produced, we notice that if you took the derivative of cost with respect to the number of units produced, which is dc over dx, it refers to the rate of change of cost with respect to the level of production. And so the C function, the cost function, cost with respect to X, so cost as a function of the number of units produced, C of X, will have number of factors that will help to arrive at the cost of producing something. So let me write here in pure mathematical terms and explain it to you. I'm using Greek letters here. Okay, alpha x cubed plus beta x squared plus gamma x plus delta. This is another delta. You know, like in English, we have uppercase and lowercase in Greek. So this is another delta. The triangle is the other delta. That's the uppercase delta. So what we see here is that wherever you have the x, right, the x indicates the number of units produced. It depends on what your product is. So whatever the product is, how many you produce. But this delta here does not have an x, which means that refers to the fixed costs. And the fixed cost could be anything, like, you know, like rent. So whether you produce something or not, that facility which you use for your production, you'll have to pay the rent. The equipment, right? Whether you produce anything or not, you have to invest in the equipment. So all these become the fixed costs, payroll, all those things. And then other things can vary, okay? Even the pay can vary because it depends on the labor, right? How many people you employ, for what season. So it again depends on many things. But all these three, the ones that have the x's in them, they are variable costs because you have the variable involved in them, right? And when I say variable costs, it could be the raw materials, because that will keep changing, right? You can think of taxes, that varies based on the number of production, and labor and so on. Fixed costs, no matter what you produce or what you don't produce, you'll have to pay them, right? So then we can think of rent, heat for that facility, equipment. You can go on like that. And if you actually look at the management and all other things that go into fixed costs, it's really a lot to run a business. So I honestly have great respect for those who run business, because it takes in, they have to absorb a lot of costs before they begin to turn profit. So anyways, so that is where we see it in economics. I'm going to come back with a problem so that we can actually see how to interpret these things in from an economic standpoint. Just before I proceed to the next problem, I just wanted to kind of explain a little more on the marginal cost so that it will help you with the interpretation. Okay. Now we said C of X is this represents the dollars, right? The cost needed to produce X, let's say X tons of steel in 1 week. Okay, that I'm setting up a scenario. So it's the cost, the dollar amount needed to produce X tons of steel in 1 week. So if I were to produce X plus H tons of steel, it implies it's going to cost more. Very clearly, you can see that. And this is for per week. Okay. So if I want to find the cost difference, what is the cost difference in what I produce regularly each week versus extra or additional tons that I have to produce each week? The cost difference, okay, it will be the average cost for each additional item, in this case each additional ton, divided by H, because H is the extra, right? X plus H, that's the extra that you are doing. So if I were to kind of put it for you in the expression we are familiar with, cost of producing X plus H tons of steel minus the cost of X tons of steel divided by H tons of steel produced will be the average cost for each of the additional H tons of steel produced. Yeah. I apologize. I put the over H here. It should have been here. Okay. Now that makes sense. So cost difference, right, divided by H would give us the average. Because it's the average, I have to divide it by H, isn't it? Because that's the extra or additional tons of steel we wish to produce. And so this, when we try to take the limit of this ratio, because you're trying to find the marginal cost, right? So if you want to find the marginal cost, then you have to allow that H to be 0, meaning you don't have any extra. What happens if you didn't produce extra? So the marginal cost. So limit of Cx plus H minus C of X all over H. Remember, this is limit of the dq, basically. Right? This is your dC over dx. And that is known as the marginal cost of production. Marginal cost of producing more steel per week when the current weekly production is X tons. In the current So you can kind of understand how it's important for businesses to manage their costs when we have an extra order placed. So even right now, right, when we see the emergency situation like the pandemic situation, all that, when they were trying to mass produce more masks, there was an initial challenge where you had to adjust all these things and then begin to produce them. So there is definitely a small reaction time that needs to be given to start producing. Now this situation was very different because it was an emergency. But if we are thinking in terms of running a business, you really have to compute the cost it takes to take on additional production. So it's not always that additional production will result in additional profit. Okay, because you always want to know if the demand will remain, even if you go more than what you usually or currently produce. So this calculation helps businesses to estimate their cost, and so it's really important, the understanding of derivatives in business. And now we are ready to go into our problem. Suppose that the dollar cost of producing X washing machines is C of X equals 2000 plus 100X minus 0.1X squared. A, find the average cost per machine of producing the first 100 washing machines. B, find the marginal cost when 100 washing machines are produced. And C, show the marginal cost when 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 has been made. Okay. So let's go one by one. Let's start with A. So we are asked to, we are given C of X to be this. The average cost, okay, so before we find the average cost, let me find what is the cost of producing first 100 washing machines. So plug in 100 for X. And that gives us 11,000. Okay. Now this is the cost of excuse me, cost of 100 washing machines. So the average cost, so I'm just going to write CAV, or average cost, will be this 11,000 divided by the 100 washing machines, right? So that comes out to be 110. So the average cost per machine of producing the first 100 washing machines is $110. Okay, find B is to find the marginal cost. And we know that marginal cost is C prime of X, right? So then one more time, let's write C of X. C prime of X, the derivative of this would be 0 plus 100 minus 0.1 times 2x. Yeah. That's basically 100 minus 0.2x, C prime of X. But they wanted us to find the marginal cost when 100 washing machines are produced. So marginal cost of 100 washing machines will be 100 minus 0.2 times 100. Plug in for X as 100. That gives us $80. The marginal cost of producing 100 washing machines. C is, we need to figure out what is the cost of producing one more washing machine after the first 100 have been made. Okay, so we already know the marginal cost for the first 100. So let's go ahead and compute that. So I'll say the cost of producing the 100 first washing machine is cost of 101, the 101st or 101 washing machine minus cost of producing 100 washing machines, right? Okay, and this one, when we compute this, so plug in for for x as 101, that computation gives us 11,079.9 because its cost was 90 cents, minus this one we found out earlier, right? You can see here in part A, found that to be 11,000. So instead of 100, you do 101 to get the first part. And so that will be 11,000, which comes out to be 79.90. And you can see that part B and part C, right, they come out to be almost the same. They're approximately equal to each other, because that's 80 and this is 79.90 when you do it manually. So the cost of producing 100 first machine is this. And instead of doing this manually, you're using the marginal cost to help determine that what happens, what will be the cost of producing additional machines once you've manufactured, based on your current level of production, which is 100 washing machines. I wanted to do this additional problem for better understanding. So here we have the profit function for a pen manufacturer to be given as P of x, because it's profit, not cost, it's profit, P of x, with 790x minus 0.3x squared, where x is the number of pens sold. Use the marginal profit function to estimate the profit obtained from selling the 500 first pen. Okay, so we can think of the marginal cost, or sorry, in this case, marginal profit, is the derivative of the profit function, right? That means you take the derivative P prime of x, and that comes out to be 790 minus 0.3 times 2x, which is 790 minus 0.6x. So if we wanted to find the approximate profit obtained from selling the 500 first pen, we'll have to find for the first 500, okay, because then anything more than that will give us that information. So P prime of 500 will be 790 minus 0.6 times 500. It comes to 490. So I'll just interpret this. Okay. So what this means is, this implies, if one more pen is sold than the current 500, pens, the profit, because it's positive, right? Positive 490, the profit will increase, because it's a slope, so it's going to increase. The profit will increase by approximately $490. This is helpful because you just did the derivative and you plugged in for 500 and you got that information. But we already saw that we could find the actual change by manually calculating it. So the actual change, to get the 500 first pen will be the actual profit, actual change in profit, I say, would be the profit function for 500 first pen minus for 500 pens. So 501 pence minus profit of 500 pence would be, this will be, so basically you're taking the 790 times 501 minus 0.3 times 501 squared. Okay, so I'll just put that here. That's what you get here. That minus, for this 500, it's 790 times 500 minus 0.3 times 500 squared. go ahead and do that. If you computed each one of them, that result comes out to be, compute it with your calculator, of course, 489.70. Okay, so we can say the actual increase in profit from selling the 501st pen is this $489.70. So then the estimate we did, right, from the marginal cost. So the estimate gave us what? $490, right? So it was off by 30 cents. The estimate from the marginal profit equation was off by 30 cents. So it's really a very interesting application when it comes to economics. So with that, we come to the end of this section in Chapter 3. See you soon.